Hello, so I am Robert Serphillips. I'm the DFT product specialist at Mentor Graphics Emulation Division. I'm going to talk to you about DFT, some of the challenges that we face in the industry, not just creating the patterns, but bringing them up on the tester, and how we can help with acceleration through the Veloce DFT app. So let's define DFT. What is DFT? DFT is the act of adding a non-functional embedded test-only logic into your device with the intent to generate patterns for delivery to the production AT. As these devices have got more and more complex, so have the types of patterns and the content within. So design for test has turned into more of an umbrella term. It contains multiple bit buckets of types of patterns that you're going to see in the field. So the first is the traditional structural test. It's your scan, your Bist, or excuse me, your AC scan, your DC scan. There's your Bist, your memory Bist, your logic Bists. Logic Bist is making a big comeback with the amount of analog you're starting to see in the parts these days. There's your parametric test. And I'll talk more about what all these different these bit buckets are in slides here in a bit. There's your I/O characterization, your data sheet compliance. And finally, there's your functional test. Functional test does fall under the DFT umbrella. But the one thing that all of these different types of patterns have in common is that they all run in product and test on the AT tester, the automated test equipment. Okay, so let's talk about structural tests. So structural test is your traditional DC scan, static scan, and your at-speed scan. So it's your DC scan is your stuck at model. You're stuck at zeros, you're stuck at ones. You're adding muxes to the front of these latches to basically turn your design into a long shift register. You shift data in, it gets latched in the register, it propagates up to a combinational cloud of logic, evaluates, gets sent back down into the next register and shifted out to generate your expect data. It's your EDT logic, your embedded deterministic test logic. That's your compression schemes, where you've got your compressor, your decompressor on the inputs that takes a compressed stream of inputs and ones and zeros, decompresses it, sends it out to your scan chains. ATPG pretty much generates most of these patterns because they're so compressed and so complex. There's also your at-speed scan. Basically, it's the same exact thing, but now you're using the onboard PLL, and it's your slack model, your transition, your propagation delay, your transition faults. You're testing the input setup between the output latch and the input latch in the next position on the chain. So challenges. So I've got that one bolded because that's going to be a recurring theme here. These patterns are very, very long. I mean, it can take days, weeks, and even months to run this stuff during traditional software simulation. You've got large numbers of patterns that you have to simulate. On top of that, in order to increase your fault coverage, you may go from a pattern set that initially started at 400 patterns with 98% fault coverage to over 4,000 patterns to pick up that one last 1% or so. You've got things like multi-cycle paths that you can't scan through those. So your ATPG tools, what they traditionally do is they just mask that logic out. So now you have X's in your pattern, so you're not testing any of those faults. A lot of these SOCs, they got multiple frequency domains, multiple VDD islands, so you have to make sure that you scan only within those partitions. And finally, large DIDT events where because you're scanning all this data into these shift registers, they're highly compressed. What you could do is you could have a voltage sensitivity on one of the nets where if the rail collapses, you're going to get a false fail. Okay. Memory Bist. So memory Bist, inserted logic, just testing the large arrays. On the AT tester, when the pattern fails, you can use the output of the XY coordinates of that memory to go back and generate a new pattern to program, let's say, your fuse box, to blow the fuses, to insert redundant arrays to increase yields. Logic Bist. So Logic Bist is also dedicated logic, and it's used to functionally test analog logic, if that makes sense. But it's for things like the automotive vertical segments that have lots of high-speed analog, or even the IoT, which has these ultra-reduced pin count devices. So some challenges with Bist. Bist patterns take a very long time to simulate. Most of the time is spent waiting for the memories to evaluate, to go through all the March algorithm, things like that. These things can take months to simulate in software. Again, DIDT events, you've got, take a networking chip, for example, you may have an instance where you've got megabytes of onboard memory. The more memory you have, the more activity that's being created on the chip, the higher the possibility that the DIDT event could cause a false fail. Finally, when you get it and you run it on the tester, you have the same challenges: long test times and high test costs. And because you're only testing the memory itself, you're not really testing the boundary of the memories. You potentially have uncovered faults at those boundaries. Okay, parametric test. So parametric test is basically your analog test, right? It's if you got a crystal oscillator, you got a PLL, you want to measure things like jitter, you want to measure the VCOD, you want to see if your PLL goes in a wide open throttle, you want to make some analog measurements on a high-speed PHY, your analog to digital, your digital analog converters, you want to measure things like the bandwidth, you want to measure the resolution, you want to measure sample rate. So this slide is interesting because a lot of times, this is what's done in the lab. You don't actually do this on a tester. But the nice thing about a tester is you can do this much more cost efficient than you can in a lab setup. And you can't, obviously you can't scan a resistor, you can't scan a capacitor, so you have to start thinking of other ways to test this stuff. Challenges, again, running theme, long simulation times, a lot of analog, a lot of complexity. Also, when you run this stuff, when you run it in the software simulator, you're not going to get the actual value of the measured value of a resistor. So what's going to happen is you're just going to get false information. So you run this simulation for days on end, and it still fails. Then once you finally get it on the tester, it's not pass-fail. It's more of you're measuring, let's say you're sourcing a current into a resistor, you're feeding that back through an analog digital converter, and you're reading the digital value of that. You take that value and you set limits, high limits, low limits. Let's say it's a calibration resistor or something like that. So you're setting limits on the tester, but that's a very iterative process. You have to measure it multiple times. You have to measure it on every single device you do to make sure that the device falls within that range, or that measurement falls within that range. And a lot of that costs money. A lot of instrumentation, a lot of engineering resources, a lot of tester resources. I/O characterization. Again, this is another one that's traditionally done in the lab, but the tester has all the capability in the pin electronics already on board. So it's your data sheet compliance. You want to measure your data IVE, let's say a high-speed PCI Gen 4 or something like that. You want to measure, let's say, your input setups, your output holds, your pins, skew between two pins, your switching speed, your minimum pulse width. All this stuff can be done on the tester, and it's actually cheaper to do it on a tester than it is to do in the lab. But the way that it's done is it's mostly a functional test, where you're setting up the SoC, you're bringing out a reset, you're programming whatever needs to be programmed on the platform, and now you're sending through like a DMA functional transactions to whatever you're measuring, an SRAM or something like that. So there's a lot of complexity that goes into generating those patterns. You've got to have a functional programming model, long simulation times. Then once you get it on the tester, in order to measure something as simple as an input setup, let's say you have an output-to-output spec where you got a clock coming out of the device and you're trying to measure data coming out with it. The first thing you got to do is you got to figure out where that clock is. So you sit there and you sweep your strobes. You find out where the output is on that clock. You feed that back in. You update your timing. Now you do the same thing again for your data. So edge sweeps, clock searches, all that stuff is very time-consuming on a tester. Functional coverage. So functional coverage is your traditional, you run some programs, you write some C code, some assembly. Very difficult to do. It's always been very difficult to do. It's always been very time consuming, but if you take a design for test methodology to it and you apply test logic, you still can now run it functionally, but in a test mode. You don't necessarily have to run it in the same mode that the customer runs it in. You can put some bypass paths in your boot ROM, bypass paths in your BIOS, maybe have a 32-bit test loader, so you don't have to sit there and load it in through JTAG and things like that. So, but it's used to close coverage. So all those faults that are missed through the ATPG tools, through faults that you just can't get because maybe it's a multi-cycle path or something like that, it's used to measure power and performance. So you run your synthetic benchmarks, dry stones, wet stones, etc. And then you can measure things like, I want to put it into a low power mode. I want to see what the minimum power is. I can run a dry stone and I can measure what the power of that to get like a typical power. Most importantly, you want to know what thermal power is. You want to be able to tell your customers what kind of heat sink, what kind of fan do I want to put on this thing. DIDT events, that's another one. So a lot of times the DIDT events that you see are a cause of test. It's a cause of running Bist. It's a cause of running your structural test because you're creating toggles of you're toggling transistors in a way that would never toggle functionally. So you have some functional code, you run it just to see if those DIDT events are real or not. Some of those, sometimes they are only caught functionally. Let's say the way the layout of the design is, you got a data line and a clock line crisscrossing or something like that, and then a VDD right on top of that. So if you get the right data sequence at the right clock edge, you can maybe inductively or capacitively induce noise onto that data line and get a real fail. And then finally, speed. You want to make sure that you can measure the Fmax, the Fmin, those things. Challenges. Again, long simulation times. I've personally done some dry stones that take 6 months to run in software simulation, and that's one iteration. So you better get it right the first time because you only got one shot at it. It also takes a long time to write the code. You got to figure out how to get the device out of reset. You got to get it programmed. Also, once you get it on the tester, now that you're running functionally, you are crossing multiple time domains. You're crossing multiple voltage islands. So it is very challenging on the tester to make these things work. So that goes back to, if you take a DFT, a design for test approach to your functional, you can constrain some of this determinism that you see on the tester. All right, so summary of challenges. So this is not exhaustive, but it's a pretty good list here. SoCs are getting much more complex, multiple clock domains, multiple voltage islands. So you got to add more and more test logic to get the part to behave on the tester. That leads to an exponentially growing pattern set, and not just the number of patterns, but the different types of patterns that are required to cover all of those faults. The common challenge you're going to find with all of these things is it just takes forever to simulate these things. It's going to put your schedule at risk. Okay, so what's next? So hardware emulation is the next logical step. I mean, software simulation is just not getting us there anymore. It takes too long. It's too many iterations. You're not going to meet any of your deliverables. So what can Veloce DFT app do? We're going to help you verify all your inserted test logic. We're going to accelerate your time to market, your time to entitlement, and finally reduce the ATE test costs. Okay, so Veloce. So Veloce Strato is it's a hardware layer. So it's got multiple chassis, and each one of these chassis contain X number of gates. It scales from 256 million gates all the way up to 15 billion gates. A traditional large, let's say, networking SoC falls usually in the ballpark of like maybe 300 to 400 million gates. So this has got massive amount of expansion to it. It's an operating system that runs on top of that, as well as applications that run on the operating system. Today we're talking about the DFT app. There's information about all these other apps that I'm not going to get in today. We're going to focus on just the DFT app. Okay, so the hardware side. So the hardware side scales from a single Quattro chassis with one AVB that holds 16 million gates. And I'll get into the AVBs and all that in here in a second. But it's multi-user, so you can run these things on the LSF grid or your Sun grid, right? You just put it in there. You go to kick off an LSF job. You just change your resource string, and it just lands on the Quattro. You don't even know, or any of these machines, right? So there are multiple users. You can add multiple AVBs to each one of these chassis, and you can string them together to get all the way up to 15 billion gates. All right. so the architecture. So you take your RTL or your gate level design, you synthesize, place and route, pin assignments. It handles all the timing, your chip to chip, your board to board, your chassis to chassis. It handles all that for you, but it lands on the Crystal SoC. This is not a standard Xilinx or Altera FPGA. This is a Mentor designed and built product. Each one of those crystals go on this board. That's the AVB there, and then you take that board and you can stuff it in the chassis, and then you can string chassis together. Okay, so where can emulation help? So this is going back to the previous slide. So we can we can verify all the inserted test logic. That reduces your software simulation time through hardware acceleration. We can accelerate your time to market, time to entitlement, and reduce test cost. So let's talk about these. So logics and structures. So all of your scan chains, your scan cells, the launch flops, the capture flops, all your compression logic, your EDT logic, any functional logic that you add to the device, all of this can be run on the emulator. Same exact fashion you run it in the software simulator. So it verifies the correctness of the pattern. So at the end of the day, you're going to have a pattern. You have to ship that to the product and test groups. It's got compare data in there. You want to make sure that that compare data is accurate because there's no visibility on the AT to debug if something fails. Also, all of your DFT is done post-synthesis. So it's all done at gate level. Gate level usually comes later on in the design cycle. You start with RTL, you move on to gate. Then and only then can the DFT engineers actually begin their job. And that long software simulation time can get reduced, and it's literally a days to seconds. And I've got some metrics I'm going to show here a little bit later, but it's literally days to seconds. All right, accelerate your time to market. You're going to meet your pattern delivery schedule, your tape out schedule. A lot of times you can't tape out until DFT meets some predetermined coverage metrics. If they're not there with the metrics because the simulations are still running, tape out gets delayed. All the patterns have to be verified before first silicon and delivered at least a few weeks early so that the AT engineers have time to get all of these various patterns, thousands of patterns they're going to be working with, build it into a test program, get their hardware and everything up and running to be ready for first silicon. So you want to have day one bring up. Silicon comes in, it's the only unknown. And any delays will put customer deliveries, sample deliveries at risk. So here's a visual about what I was talking about with the gate level. So you start with the design cycle with your RTL. Now this is all at the SoC level, not at the IP level. So you get your SoC, all logic entered. You start with RTL. You start doing all your functional verification flow. Then comes the gate level. It's usually a few months later on down the road. Now the DFT can actually begin. So all of that time that could have been spent bringing up DFT now gets pushed out. Finally, once you have your gate level with all your scan inserted logic, then you start your simulations. It's already too late at that point because you've already taped out, silicon's already here, so now you're dealing with trying to debug silicon, you're trying to debug test programs, you're trying to debug patterns. None of this stuff it's all unknown, right? So that puts your schedule at risk. So if we can shorten that simulation time so that all the patterns are now verified by tape out, verified correctness, that they're correct. All right, accelerate your time to entitlement. So we want the patterns to be correct, robust, and reliable day one. We want to make sure that all faults can be detected in a design. You want to know that beforehand so that you don't have a fault or a test escape pass on the AT tester and then go out to the customer. There's no visibility whatsoever on an AT. Is there any test engineers? Anybody worked on a tester here before? Anybody? No? Okay, so the way a tester works is it's really just a hunk of memory that makes contact with the C5 at the pins, and it just drives ones and zeros into the device. The device responds and sends out ones and zeros, which are now H's, L's, and X's in the pattern. So the only thing the tester can see is what is at the pin boundary. It's not like simulation. You can't see what's going on inside the device. So when something fails, the only information that you have is it's this pattern, this line number, this pin, it should have been an X, or excuse me, should have been an H, it came out an L. So you have no visibility on the tester. Marginal patterns. So marginal patterns are one that will pass on one device, may pass on 10 devices, but once you go into production, maybe there's a sensitivity in that pattern where you start running 10,000 devices and you get a 3% fallout, 5% fallout for that one pattern. You want to make sure you can run all that stuff in advance. You make sure that it's verified as being a reliable pattern. Also, you can do power aware. So what power aware allows you to do is look at various aspects of your design and say, well, while I'm scanning this stuff in, I'm causing this DIDT event. You want to know that in advance, and that'll allow you to change the way you structure your pattern. And then probably the biggest headache you're going to get on the tester is a false pass or a false fail. So let's say you get a fail on the tester, you run it in simulation, it passes, you go down to the customer board, it passes. So now you got to figure out what's going on. So now you start this massive correlation effort between all these different cross-functional groups to figure out why either the tester's wrong, or maybe the tester's right and the simulation's wrong, and maybe the customer board's wrong, right? But that's a huge correlation nightmare. And finally, reduce your test costs. So on these larger SoCs, your test cost can be up to 40% of the device cost. It's 40%, that's pure revenue right there that's being lost. So if you can reduce your test costs, it's just free money. So why is that? So you've got more patterns, you got bigger patterns, you got lots of different types of patterns. The more patterns you have, the more memory that's consumed on the tester, which that memory is actually, it's licensed, so you have to pay for that. So if you need X, let's say you add one more pattern, and that takes you over the amount of physical memory that you have on the tester, well, now you got to buy all that extra memory. Every second on the tester can also translate into every wall time of seconds spent on the tester can be translated to test time, which can be translated to dollars, which would be your test costs. So the idea is you want the smallest pattern set possible with the highest fault coverage to minimize your test costs. Okay, so how does the tool work? So it's pretty simple. It requires a, this thing have a laser on it. Anyways, so you take your pattern, which is your style file. That's a industry standard. It's your standard test interface language. So it's a pattern. It contains all the IOs, all the C5s. It contains the vectors, the input zeros and ones, the outputs HLs and X's. It also contains timing information, whether it's a clock or if it's data, if it's a return format, if it's a non-return format, if it's a surround by. So you take that pattern, that's what's going to get run on the tester. You take that, you take your gate level net list with all your inserted test logic. You add a couple lines to the config file, telling it that it's running the DFT app. You compile it, right? You also give it the DFT netlist top. So what that tells it to do, what the Veloce compile will do is it'll create your test bench. It'll instantiate your design underneath it, make all the connections for you. It's pretty push button. All the complexity that you have of just compiling a gate level netlist for software simulation still applies, but it's the same process. It's the runtime flow. So the way this works is the same exact way it runs on the tester. So you've got your compiled design with your DFT test bench. The stimulus gets read from the style file, vector by vector, line by line, driven onto the pins. The DUT will respond and generate output. That output then gets read by the executable and compared to what's in the file to see if there's mismatches. You can run multiple patterns, just like you do on a tester. So if you've got 100 patterns that all have the same timing and test header, your pin information, you can take all 100 of those and just run it all at one time. Now, if you've got, let's say, 2 patterns that have different pin headers, then just like on the tester, now you have to recompile. So it would be a test insertion on the tester where you have to load new timing, new wave sets, things like that. Same exact thing on the emulator. You can't burst them together, which is actually nice because now you're verifying your test program to making sure you don't make that mistake on the tester. You've got a pattern that just doesn't compile. And then debug flow. So the nice thing about the emulator, same thing as in software simulation, full visibility. You can see every net. You can generate waveforms. You can see what the pins are doing. You can see when the pins are miscomparing. You can see what pin. You can load the design, double click on the fail, and trace back through the logic to see the net or the flop or whatever it is that's actually failing. You can generate these waveforms real time. So as the emulation is running, the waveform is, the database is being generated. You can pull it up in your waveform viewer, in this case it's a visualizer, and debug it on the fly. So here are those metrics. So these are real customer designs using these various methodologies: ATPG, the Bist, scan, the burn-in, wafer level burn-in. But so let's look at the wide I/O Bist. So in order to run that in software simulation, it's 83 days to run that pattern set. That's just Bist. That's not even the structural, the characterization. That's not even the ATPG generated patterns. That's just that one pattern set, 83 days to 120 minutes. That's 1,000x, right? You look at a CPU core, it's 10,000x, something that would take 12 hours. I'm assuming that's a work day, not a regular day, but that's something you can do in 4 hours, you can do in 5 seconds. So now you can do multiple iterations of this thing instead of starting the simulation, going home for the night, or 3 months later coming back and seeing it. Okay, so to summarize, like I went really fast through this, but that's good, we'll be back on track. SOCs are getting more complex, higher gate count, more time domains, more voltage islands. Pattern sets are getting bigger, more diverse. Traditional software simulation puts your time to market, your time to entitlement at risk. With Veloce, we've got the gate count, and we've got the performance. We support the industry standard style pattern format, which any tester can read that. It doesn't matter if you're on a Teradyne or an Advent test, or any of the testers can read style. And it's a days to seconds emulation. Thank you.